Okay, come. This is going right.
So, hi guys. Let's write a code snippet for code snippet which takes log n time. So we all know that after O of 1, which is constant time, log n is the most efficient time complexity. So what exactly is log n time complexity? If basically time complexity is the amount of time which a program is going to take as a function of its input size. So if n is the input size and if f of n is the time complexity, the log n graph goes like this, where increasing n wouldn't have much of difference in the time complexity. So for that reason, log n is efficient. When is log n possible? When the input size is being half every time, like in each iteration, if the input size is being half, then log n is possible. Let me think of as a code. So yeah, binary search guys. So binary search is obviously an algorithm which takes log n time because the input size is going to be half in each iteration. Let's just say I have an array, a sorted array by the way. 2, 3, 4, 5, 6, and 9. And I am searching for, say, 6. So I could have two pointers, like the low and the high. So the low is pointing towards the index 0, and the high is pointing towards n minus 1, where n is the size of the array. Basically, how do you search for an element? If it were linear search, what will we do? We just iterate through each of the element, and when we find our key, we just return that. That's it, right? But binary search is an amazing concept which our sir has taught us. Basically, we could have a mid, an approximate value of this whole array. So the approximate value, if it is sorted, is going to be the middle value, right? So that is going to be low plus high by 2. Like the position is going to be low plus high by 2. So 5 plus 0 by 2 is 2, right? So I can have this as my mid. And I'm going to check if this, like the element inside the mid position is the element which we are searching for. So let's say I'm searching for 6, right? So is 4 equal to 6? No, right? So is 6 greater than 4? If 6 is actually greater than 4, then do we have to search for elements to the left of 4? Do we have to search these elements? There's no need, right? So this is the concept of binary search. We don't have to search for search towards the left of the mid if we know that the element is greater than the mid. Sorry, the element inside the mid position. So what will the code be like? Obviously, then when do I say that I didn't find my element? When the low and high they cross each other, right? So that's when I'll be like, okay, I didn't find my element. So let's say int binary search. I have an integer array, and I'm finding for a key. So my first task is to calculate a mid, right? So whatever, okay, wait, let me also pass, okay, no need. So let's just say int low is equal to 0 and int high is equal to n minus 1. I'll just compute a mid, which is int mid is equal to low plus high by 2, right? So I just iterate, I just keep lowering my low value, and I just keep increasing the low and decreasing the high. There will be a point where the low and high they cross each other, which means that I didn't find my element. So why? This is the main logic. Low is less than or equal to high. What I'm actually going to do is I'm going to compute the mid value, and I'm going to check if that element is equal to the element inside the mid is equal to the key I'm searching for. So I've done a mistake. Can you spot it over here? Moving.
Need not to compute.
Okay, we need not compute the mid in the first place over here. That will be inside the loop because obviously, guys, like it has to be in the loop, right? So yeah. We compute the mid inside the loop, and mid is equal to low plus high by 2. What we'll actually do is we'll check if the element inside mid is actually equal to the key. So if a of mid is equal to key, what do we do? We found the element, guys, so we return that element. Return key. Now, let's say my a of mid that is less than the element I'm searching for. So we did not search like for that element towards the left of mid, right? So let me just update the low value to mid plus 1. So the code goes like, if a of mid is less than key, the low value is going to be low plus 1. Sorry, mid plus 1. Right. Now, what if my a of mid is greater than key? So then obviously I'm not going to search for the element towards the right of the array. So I just update my high value to mid minus 1. Else high is equal to mid minus 1. Now, what if we don't return, what if we don't find an element? So after all this while I'm going to return minus 1. So if the element exists, if the key exists in the array, the key is going to get returned, or else minus 1 is going to get returned. Thank you, guys.
Good students. So here, if the elements, the number of elements he has taken is 2, 3, 4, 5, 6 and 9, right? The total number of elements he has taken is 6. So for linear search, he will be doing the comparison of 6 elements, that is big of n, right? And here he will be keeping on dividing. So 6 will become 3, 3 will become 2 will become 1, right? That division actually makes that algorithm runs with a time complexity of big of log n. And one thing is here, the elements that you have to give is in a sorted order. So here, first you have to pass the elements into a sorting technique and then go for binary search. For linear search, nothing like that, which the elements can be in an unordered order. Okay, thank you. Okay.
Thank you.
Thank you.